Okay, today's topic is titrations. So let's start off with a definition. We know that acids and bases react with each other in neutralization reactions. When this is done under carefully controlled and carefully measured conditions, we call this a titration. Okay, so when we carry out a very carefully measured neutralization, it's called a titration. The purpose of the titration is to determine the concentration of an unknown acid or base. To do this, we start with what's called the standard solution. The standard solution is the one that you know the concentration of. So, in other words, if you look at my setup here, this burette contains the standard solution. So we know the molarity of what we're putting in the burette. Okay. In the lab that we carry out tomorrow, we're going to have a standardized solution of sodium hydroxide, and the molarity will be known, so you'll be told the day of. Okay. Now, in the beaker, this is where the reaction takes place. So what we do is we put in the beaker the acid or base of unknown molarity. All right. So I've got this acid that I found. I don't know the molarity, but I can use a known solution and stoichiometry to help me figure it out. Now, we also use an indicator. And as you know by now, indicator changes colors when something turns to an acid or base. So in a typical scenario, if we are putting an acid in here, like hydrochloric acid, the main indicator that we use in lab is called phenolphthalein. Do you guys remember what color phenolphthalein was in acid? No change, right? Clear. So it starts as a clear solution, in neutral solution, and an acid solution. But phenolphthalein turns pink the minute something turns basic. Okay, so imagine this, right? Here's my acid, and I'm adding a base, sodium hydroxide, and the more base I add, the more liquid that's used up, right? And so we can actually measure the lines on here to determine the volume used, because we can just read it. So if we know the volume is known and the molarity is known, what quantity can you find when you know the volume and molarity? Moles. We can find the moles of base that was needed. And we will know the volume of the unknown is measured ahead of time, which means that's known. So we use the volume, we use the molarity of the standard solution, we get the moles, and then we use a balanced equation. So your typical balanced equation is HCl plus NaOH, right? In most cases. We've already established that we get water and a salt. The mole ratio between HCl and NaOH is 1:1. So however many moles of base we use, that tells us how many moles of acid there were. And then I can find the molarity in here because I have measured the volume. Okay, so let's go into a little more detail. That's kind of the overview. Phenolphthalein is clear in acid when base is introduced to the mix. We know that phenolphthalein turns pink in base. And so here we see that kind of the pink cloud form. This will turn pink for a second, but if you swirl the flask, the pink will go away. Because after a couple drops, the base that you added was neutralized by all the acid that was in here. That's why that's why it'll go back to being clear. When the solution is no longer clear, meaning when it stays pink, if it stays pink, that means no acid is left, only base. And that's when you stop the reaction, once it's permanently pink. So we are using an indicator to tell us when to stop adding solution from the burette. It's pretty handy, right? So it's very clearly, it's clear or it's pink. Once you see it stay pink, you're done. And then, we'll record our measurements, and then we'll do another trial. We'll do this a couple of times, and we'll take an average of the trials. Okay? All right, so a couple of other terms. The term equivalence point is the point when you've added exactly enough base to neutralize the acid, or in other words, it's when the moles of the acid equals, oops, that's not plural, equals the moles of the base. Don't worry too much about this graphic. We used to go more in depth with this graphic, but we're not going to really even bring it up. Now, the other term that's similar to equivalence point but is not the same is what we call end point. It's very different. The end point of the titration is when the indicator changes color. Now, I know I just said that we were done when the solution changes from clear to pink, so ideally, the equivalence point is the same as the end point. But usually it's close, but not exactly the same. Okay, so what I mean by that is this. I know it's kind of confusing. So when I say equivalence point, when I say end point, this can be referring to two different things. It could be referring to either pH or volume. So, for example, if in the previous picture here, if we get to this color change, the fact that I'm calling it a color change means this is what? Is this the equivalence point or is this the end point? This is the end point. So this end point will take place at a pH of about 9. Ideally, I would like to stop adding base when the pH is at 7. So 7 and 9 are pretty close to each other, at least on a graph, because if I look and see where's the pH of 7, where's the pH of 9, if we track this down, how far apart are those two volumes on the x-axis? Are they really far apart, or are they really close? They're really close. They're really close. Okay. All right, so the equivalence point is when the moles are equal. The end point is when the indicator changes color. The indicator that we are using is phenolphthalein, which changes color at a pH of 9. pH of 9 is close to a pH of 7. Now, you might be thinking, well, why don't we use an indicator that changes color at a pH of 7? Wouldn't that be more exact? Because we want it to change at a pH of 7. Why don't we use one? So here's the answer. Not all indicators change color at the same pH. The one of them that does change at a pH of 7 is called bromethymol blue. It starts as a yellow in acid and turns blue in base, but here's the problem. It goes from yellow to yellowish green to yellow green to green to green to green blue to green blue blue to aqua to blue. There's too much judgment involved in deciding what green is. It's too hard to discern. Not everybody has the same interpretation of green. So it's better to use something that changes a little bit differently, but is clearer to interpret. It's easy for everyone to see the difference between clear and pink, but it's hard for people to discern the difference between yellow, green, and green. Does that make sense? Okay. So anyways, here's the point of a titration. The point is to calculate the molarity of an unknown. So let's walk through this example. We know that 1 mole of hydrogen ion, that's this, can neutralize 1 mole of hydroxide ion, which is this. Right? We know this because we can write a balanced equation. We can write either this, or we can write it based on the actual reactants, which is HCl and NaOH. Either way, the ratio is 1 to 1. Okay, so I have a balanced equation. Determine the mole ratio for a hydrogen ion and hydroxide ion. So like I said before, it's 1 to 1 here, right? And it's also 1 to 1 here, 1 HCl for every 1 NaOH. So both of these reactions are telling us the same thing. Okay, so it's 1 to 1. Find the moles of the standard solution. So let's go back to the prompt here. We have a 30 milliliter sample of HCl, and we neutralize it during a titration. We used 28.92 milliliters of 0.150 molar sodium hydroxide. Find the HCl molarity. All right, so you can only find moles for the species that you have both the volume and the molarity of. That's this guy right here. So, like you learned last unit, if you multiply the molarity by the volume, you can find the moles. And milliliters has to be converted to liters for this to work. All right, so 0.004335 moles of the standard solution. Can you guys tell me which one is the standard solution? Is it the NaOH or is it the HCl? Remember, the standard solution is the one that you know the concentration of. It's going to be the sodium hydroxide, yeah. Okay, so we have the moles of the standard solution. Let's use the mole ratio to figure out the moles of the unknown. So 0.004335 moles of NaOH. Our mole ratio says there's 1 mole of HCl used for every 1 mole of sodium hydroxide used. So 0.004335 moles of HCl are what were present. Okay, and this step right here, is due to the volume at the equivalence point. Right? This volume right here, that's the key. And that volume is what you're going to read on the burette. So when you're in lab and you're dispensing from the burette, when you stop adding the standard solution, you're going to read the burette, you're going to find a value, and that value is what's needed to find the moles. And then you can use the mole ratio here. Okay, and then the last step, they wanted the molarity. the molarity of HCl. So we need the moles of HCl, 0.004335, divided by the volume of HCl, which, to find the volume of the HCl, you have to go back to the beginning of the problem. You were told how much was sampled. 30. Yeah, 30. But in liters, so 0.03 liters. Okay, so 0.1445, however, sig figs makes a return appearance, and we need to look at the values that we were told. This number here has 4 sig figs, this has 4, this has 3, because the leading 0 does not count. So our answer will have 3 sig figs. All of the math in this unit, besides the logs, you learned how to do last unit. This is solution stoichiometry. It's applied. All right, so hopefully that will make you feel more comfortable with it. Okay, so this is the end goal. We found out the molarity of HCl was 0.145 molar. How did we figure this out? It's because we added standardized base until the color changed and stayed that color. When the color stayed that color, we recorded the volume, and we used that volume and the standard molarity to find our moles. We used the mole ratio to find how many moles of acid there were, and then we divided by the volume. Okay. Try this one. See if you can get to the molarity here on this practice problem. It's the same balanced equation, so you can just use the same one as before. What do you think, guys? Do we have a molarity? What'd you get? Yeah, 1.05, 1.1. So let's go through this. We've got 0.1 liter times 0.5 molar, which is 0.05 moles of NaOH. This was a 1-to-1 ratio, just like before, because it was the same balanced equation. So that means we have 0.05 moles of HCl. And they wanted the molarity. The volume of HCl is right here. So divided by 0.0450 liters, we have 1.05, but we're going to be restricted to 2 sig figs, so 1.1. Okay. So a lot of titrations have a 1-to-1 ratio, but not all of them. And so if they don't have a 1-to-1 ratio, you have to be prepared for it. You have to know how to solve it. And that's pretty easy to do as long as you have a correctly balanced equation. So here, I'm going to be reacting potassium hydroxide and phosphoric acid. So KOH, that's my base. Is KOH a strong acid or a strong base or a weak base? It's strong. You guys remember the other strong bases? They're all related. Sodium hydroxide, potassium hydroxide, Ba, Sr. Yeah, I thought I said Na, Li. It's like that little lightning bolt there on the left-hand side. You guys see it? Looks like that. Li, Na, K, Ca, B, Sr, Ba. Okay. Anyways, so KOH plus phosphoric acid. Is phosphoric acid a strong acid? Is it on the list of 6 strong acids? No, it's not. It seems like it would be, right? This is neutralization, so we get water and we get a salt. Mind your charges. Phosphate is a -3, potassium is a +1, so make sure you write that formula correctly. And then we balance this, so we're going to need, let's see, 3 Ks, so put a 3 there. That means 3 OHs, so we'll put a 3 there. That means 3 H's, which we have, and 1 phosphate, which we have. Okay. So during acids and bases, I think it helps to write the formula for water as HOH. Of course, you can write it as H2O, because that's what it is. But by writing it as HOH kind of helps you highlight how many hydroxides there are. It just kind of makes it easier to segregate the two and count them. But it's up to you. It's not wrong if you do it the other way. It's fine. All right, so here's our balanced equation. We've got this much of this molar, so that means KOH is our standard. So 0.02405 liters times 0.200 molar. .00481 moles of KOH. So that's how many moles of the base were needed to neutralize the acid. The ratio, because we're solving for H3PO4 now, is 1 H3PO4 for every 3 KOH. And this is why we balance the equation, because we have to see that we have to divide by 3. Okay, so that's going to be 0.00160 moles. I have the moles of the acid. To find the molarity of the acid, I need to divide by the volume of the acid. What's the volume of the acid? 0.024. Okay, so molarity is equal to 0.00160 moles over 0.024 liters. .066806. Let's go back and do a sig fig check. How many can we have? We got 3 numbers that we were given. Which one has the fewest sig figs? What's the lowest number of sig figs? It's 3. So 0.0668 molar H3PO4. Okay, that is a titration calculation. How are we doing? It's solution stoichiometry. That's really all it is. All right, and with a little help of indicators to tell us when to stop reacting. Okay. So that's enough.